So now let's prove the following formula. So whenever you have n plus 1 real numbers, a0 up to an, then actually it turns out that for every sum of this form, we have a very nice and compact formula for the sum. And essentially those series are called telescoping series. Why? Because we have lots of terms here, right? If we'll write them out. But then essentially it collapses, right? Like a telescope. If you think of an old model of a telescope that would retract and then collapse, right? Or retract backwards, then something similar we have here. So essentially we have lots of terms here, and all of those elements appear in the summation, but essentially it depends on the last term and the first term. And similarly, if we just switch the sign, it's basically the same formula. Here we have an element and its predecessor, and here we have an element and its successor in those elements, right? So basically here we switch the sign, so here it's the last term minus the first term, and here it's the first term minus the last term. And so the most general context in which where this would hold is that whenever we have an addition operation, for which we have an inverse, we have the zero element, and it is associative. So the most general context for this result would be for any abelian group, but it doesn't really matter here. So you can ignore what I just said. It was just a side remark. So let's prove this formula, and we'll give a couple of proofs. So the first proof is the hand waving proof, which is very satisfying, I would say. So if we were to take the sum, right, and we would just write all of the elements in this summation in this way, right? I prefer writing this way because I think it's more formal, but just to get a feel of what is going on here. So as you can see, here we have the term a1, and here we have the same term a1, but with a negative sign, so they will cancel out, right? And similarly, we have this a2, and if we had another term written out here, and then here we would have this a2 with a negative sign. And similarly here, we have this term an minus 1, and here we have the same term with a negative sign, so they cancel out. So basically all terms here are getting cancelled out except for a0. Yeah, we have no other bracket where it can cancel. And a n, right? So after canceling everything out, we have what we remain with, right? This is essentially what I've said verbally, right? If I were to add another term here, then this a2 would reduce with this a2, and then this a3 will be reduced with a term here. So essentially all the terms will get cancelled out except for an and a0. So therefore, the hand waving proof says that this is the sum, right? And I called it the hand waving proof just to state the motto of this channel, because it's called Maths, Physics, and Engineering. So the motto of this channel is that physics should be taught with mathematical rigor, but on the other hand, maths should be taught with intuition from physics. So of course, this is not related to physics, but those kind of proofs where you, in a hand-waving manner, see what's really going on is very insightful, I think, and I will not shy away from those types of proofs here, although provided that I will always bring the rigorous proof. So to make this rigorous, right, to understand what's really going on here, we need to prove this by induction, right? The only thing that we lack here is to say, well, we can continue inductively. So suppose this n equals 1, then the statement in this case is obvious. Why? Because if n is 1, then we have only one term in the summation, so obviously the formula is valid, right? Okay, and so now we make the inductive hypothesis, and we assume that this formula is valid for some n that is greater than 1, and we're going to prove this formula for n plus 1. So essentially, let us compute. So suppose we have now a sum with n plus 1 terms, right? And so we can now write this in the following way. So we will write the sum of the first n terms, and then we will add the last term here. And now we're going to apply the inductive hypothesis to this term, right? So essentially, by the inductive hypothesis, we know the value of, by the inductive hypothesis, we know the value of this sum. It is an minus a0, the last term minus the first term. And now we're going to see the same phenomena once again. So this an is going to get canceled out with this an, and this n plus 1 is going to remain, and so is going to remain this a0. So the sum is going to be that. So here's another proof, which is very rigorous. And I want to show you a third proof, which is more useful for the index shifting method that you're going to see in there. So now suppose that we have this sum, right? And so this sum can be separated in those two sums. And so from this sum, I will separate out the loss term. And from this sum, I'm going to separate out the first term. So this sum equals to that, and this sum is equals to that, right? And so essentially, I'm going to rewrite this as this an minus a0. And then we're going to have those two summations. And as you've probably guessed, those sums involve exactly the same term, right? So essentially, those are going to cancel out, to get canceled out on this massive scale at once, right? So essentially, the trick that we need to do here is to shift the index, right? So we're going to substitute L equals k minus 1 for this term. And then what we're going to have is that for this sum over here, right, this sum as k goes from 2 up to n, if k is L minus 1, so here we're going to have a L. If k is 2, k is 2, then L is 1. Sorry for the mistake, it's supposed to be L. And when k is n, then L is a minus 1, right? So the summation here is, of course, over L. So now if we now were to substitute this, right? So we have this summation, and essentially, yeah, here I didn't make this mistake. So essentially this sum equals to this sum, and this variable L and K, those are dummy variables to indicate summations. So we see that this sum involves exactly the same terms, so they exactly cancel out, and we get the same result once again, right? So now let's see some examples of how useful this formula actually is. So now let's compute or find the formula for this sum. And you may ask, well, how is this related to telescoping series? As it turns out, this term can be written in the following way. Basically, if you compute the common denominator here, then you're going to have n plus 1 here and n here, and the denominator here is going to be the product, right? So n plus 1 minus n is just 1. And basically for this sum of this term, it's already the telescoping series, we have a formula. So it's going to be the first term minus the last term. So it's going to be that or that. And we have computed that quite effortlessly. And another example which I want to show with the telescoping series is this summation, which is far less trivial. And it involves quite an ingenious trick. But we're going to see it anyway. So it's not very easy to think of this trick, but the way to think about this trick is actually more related to the sum of the geometric series, about which we're going to talk about. And this can be solved using geometric series in the earliest formula, but this is just as a promo. Okay, so now let's do the following trick. So let's write this sum in the following way. So basically what we have here is this terms, this is getting cancelled out as this, so it didn't change the summation. And now the idea is to use the identity of the difference of cosines. So essentially, I'll have this minus here. So we can write this expression over here as, if you take into consideration this minus, as this difference of those cosines. And essentially we're now back to the case of the telescoping series. Why? Because if you were to replace the n in this term by n minus 1, you would arrive to this term, right? So essentially, we already have the formula for this sum. It is again going to be just this minus, and it's the last term minus the first term, or the final result is this, right? So basically, we're able to compute the sum, okay? So now let's have an informal discussion here and ask the following question: could we have an analogous formula for the product? And here I want to use the logarithmic function, because if you're watching this video, you're probably familiar with this function. So this function is going to be introduced very rigorously in the later stages of the course, but I just want to use it here to demonstrate an idea. Basically, the idea of the logarithm, that it can take differences into quotients and summations into products. So if I want to derive the formula for the product, let's see what we can do here. So suppose that this ak is the logarithm of some ak. Basically, we need those ak to be those capital AKs to be non-zero for this to be defined. And essentially, let's just ignore of the technicalities of when does it work and see what we can derive with that. Right, so let us consider this summation over here. Right, so the log of a quotient is the difference of logs. And basically, we can already see the telescoping series here. So for this, we have a formula, right? It's the last term minus the first term, and the log of a difference is a log of a quotient. Sorry, difference of logs is the log of the quotient. And now we can also use the fact that sum of logarithms is actually the product, right? So the sum of logarithms is the logarithms of the product, okay? And so now it is supposed to be equal to that. So ignoring all technicalities, we would expect that formula of this type should hold. And indeed, we're going to use similar methods to derive the formula for the product. And this formula is also going to be very useful in the future. So now let's prove this statement. So suppose that a0 up to an are non-zero real numbers. Then we have the following formula. And probably the most general context where this would hold is whenever we have a multiplicative inverse and we have non-zero elements, right? So something like a multiplicative abelian group, right? But never mind, just ignore it. This is a course on real analysis, so we're going to think of real numbers here. So we have this statement, right? So it's the quotient of the last term by the first term. And so the proof is very satisfying. The hand-waving proof is very satisfying, even more satisfying in this case, because if we were to write out this product in the following way, then we can already see that this a1 is getting cancelled with this a1, and this a2 is going to get cancelled with this a2. Similar idea, and this an minus 1 is going to get cancelled out with this an minus 1. And so the result, right, we're going to cancel terms, except for this term and this term that are not going to get cancelled out. And so we derive the formula for this product, right? Very similar. Right, and so the formula proof with shifting indexes would go as follows. So we'd have this product, then by the property of products, it would be the product of the elements on top and divided by the products of the elements on the bottom, right? And then we're going to do the following trick. So we're going to extract the last term in the product upstairs, and we're going to extract the first term downstairs, right? And then we have those two products. Essentially here I'm going to shift the index and see that this product is the same as this product on the top, which you can probably already see by yourself, right? So, but this method of shifting the indexes is very important, so I want to overemphasize it here. Okay, so we have those products. This has already been proven. And so now if I make the substitution of L equals K minus 1, so K minus 1 becomes L here. And when K equals 2, then L equals 1. And when K equals N here, L equals N minus 1. So we get this product. And essentially, K and L here are just dummy variables to indicate the product. And so this is getting canceled out with this, right? Providing everything isn't, provided all terms are non-zero. And we get this formula once again, now with a formal proof, right? So now let's prove the formula for the geometric series. And you may ask yet again, well, how is this related to the telescoping series? And the answer you're going to see shortly. So I would say that this is true for every q that does not equal to 1. And the only reason that I say it here is that because I don't want to talk about what happens when you try to substitute 1 over here, you essentially divide, it's 0 divided by 0. So of course, we already have developed the limit theory, and we can actually resolve this limit. So if you take the limit as q approaches 1, then you're going to see that the result is supposed to be, here we have n plus 1 terms, so it's supposed to be n plus 1 or n terms. No, sorry, we're going to have n terms here from 1 up to n minus 1, so we're going to have n terms here, and so the limit as q approaches 1 is going to be just n, right? But let's ignore this. Suppose the q is not equal to 1. And another thing, I would also say that suppose the q is non-zero, just, I don't know, here, if you use, the reason that I wrote the summation in this form, right, just I wrote it out explicitly in this way, which is less formal. I prefer summations here, because if you were to try to plug in 0 instead of q in this formula, then you would have something as 0 to the power of 0, which is undefined. But then if you think of it as this sum representing this, so for every q, right, we assume that the first term is 1 here, then it's well defined. All right, so now let's proceed. So let us denote by s this sum. And now we're going to perform the following trick. We're going to multiply s by 1 minus q. So we're going to multiply this product by this sum by this. And essentially, we can insert this into the summation. What we're going to have here is, when we open it up, is again the telescoping series, for which we have already the formula ready for us, right? So all that remains is that to say that q is not equal to 1 by assumption, and then we can divide by 1 minus q, and then we have the same formula for the geometric series, right? So we've used the formula for the telescoping series to derive the formula for the sum of the geometric sequence, which is very useful. And on top of that, so here, this is valid for q which is not equal to 1, and as q approaches 1 in the limit here is n. But there's another formula that is valid for every q, right? And this is the well-known decomposition formula. Essentially, if we were to now write it out more carefully, basically we've took the sum, we've multiplied this by q minus 1, and we have shown that this equals to q to the power of n minus 1. So we have actually proved this decomposition formula for this polynomial that decomposes in the following way, and this holds for every q.